This year, our team went above and beyond to push the limits of autonomous programming, exploring exciting and unique solutions.
We created and developed a Python application from scratch that we call a path planner, which allows the user to lead a virtual robot through a set of movements, which is then used to automatically generate code. The program achieves this by providing the user an interface to perform actions such as move the robot, automatically shoot rings by calculating RPM and angle, and manipulate wobble goals. It then records the movements of the robot, parses these movements into code, and directly writes the code to the robot. The program creates a graphical representation of the robot's path to coordinate our autonomous paths with our partners. The path planner has allowed us to create a working code for the robot in a matter of minutes as compared to the days it previously took. For our path planner to be successful, we needed to make sure a robot executed commands to move exact distances. To not overshoot while moving at high speeds, we created an acceleration and deceleration function, which uses the free spinning wheels to calculate the error to a desired position and outputs power to feed the motors. We also correct for angle using a function that proportionally applies power based on an angular error. To calculate distance, we used free spinning wheels which return rotations that we then convert to inches. Traditionally, robots execute pre-planned code. However, in an effort to redefine autonomous programming, our team found a way to convert driver movements into code that could be run on the robot. The solution that we came up with records the various velocities of all the motors and positions of the servos and associates these values with a timestamp. It then stores these lists of values in a file in the robot. We then are able to read and execute this file during an autonomous period. The driver control planner is a great tool for creating autonomous programs live. We can even have our drivers plan an autonomous while the Alliance robot plays out their autonomous, making sure our programs work together flawlessly.
To detect rings in autonomous, we created a pipeline that starts with a picture from the camera on the robot. It converts it to a bitmap, an array of pixels that each have a BGR value. However, BGR represents light as a combination of the three values, so it is difficult to account for different lighting conditions. The second step in the pipeline is to convert to HSV. Value accounts for light, and saturation accounts for how vivid the color is. By thresholding for the entire range of value and saturation, we account for all light settings. The next step is thresholding. You run each pixel through a filter and focus on the hue or color of orange. We then convert each pixel to a binary value of 0 or 1 as shown on the right. We count the binary pixels to determine the number of rings on the field.
To maximize the amount of rings we could score, we took on the ambitious task of shooting from anywhere on the field. This requires two things: knowing our position on the field and using it to calculate the angle and RPM of shooting. To do this, we used dead wheels, free spinning wheels that use encoders to record distance. We developed a set of formulas that allow us to find our position using these three wheels. We used the difference between the two vertical wheels to find angle. We also use the horizontal and vertical wheels to find vectors along the x and y axis of the robot. After converting it to the frame of reference of the field using the angle, we are able to find the robot's displacement. A function then calculates the necessary angle to shoot based on our position. We also plotted out various RPMs and created a linear function based on distance. We created a series of driver enhancements which use the sensors to ease the driver's experience. For power shots, we have a button for 3 specific angles so it automatically turns to shoot all 3 power shots. We use a built-in proportional and feedback controller which adjusts the shooter RPM based on the error, allowing for accurate shooting. We also use the angle from the dead wheels and the vector-based math to shift the frame of reference of the robot and create a driver program which moves the robot relative to the driver. We used a distance sensor to detect the number of rings in the robot and stop the intake.
Thanks for watching. Please refer to our engineering portfolio and our control award submission if you have any other questions.